Okay, so we said that for nonlinear pharmacokinetics, we're just going to assume this simple model. We're going to treat it like it's an IV bolus dose. And then elimination, we said that we'll describe using the Michaelis-Menten equation, which the Michaelis-Menten equation is Vmax times C over Km plus C. And we talked about all of these components of Michaelis-Menten equation the last time that we met. Okay? Vmax and Km, and C is the plasma concentration in the model. So we took this equation and we did a couple of transformations. One said that if we multiply through by the volume distribution, we could write an equation that says that what I'm calling the daily dose. The daily dose is equal to Vmax, this is a steady state, times C steady state over Km plus C steady state. We call it Vmax prime, okay, because this Vmax and this Vmax are not the same value, okay. This second Vmax, which I call Vmax prime, and in your textbook, you're not going to see no Vmax prime, you're just going to see Vmax, but please understand that this Vmax is in terms of concentration per unit time. So this might be like micrograms per mil per hour. This one is in terms of mass per unit time, because I multiplied through the top equation by the volume, if you recall, from the last time we met. And we said we're at steady state, so we dropped the negative sign. Because a steady state, okay, there is no net change in the concentration or whatever. We're, in this first equation, that's just assuming we gave a single dose, so the concentration would be decreasing, so we got a negative sign. But once we reach steady state, the concentration reaches some steady value, so we don't need the negative sign. This is an important relationship for what we're going to be doing in lab today and the rest of our time with this model. And then we took this equation, okay, and we did a couple of steps that I outlined on the board. And we also made another transformation that says that if we look at the daily dose on the x-axis, we said that was equal to Vmax plus daily dose times Km. I think I just did something wrong, but I'm gonna let you tell me what I did wrong. Km over C steady state. What's wrong with that equation, sports fans? Beautiful. Who said that? Okay, that's good. Somebody's looking at their notes, or they looked over them, or whatever. So yeah, that should be a minus sign right here. Thank you. That should be a minus sign, such that if we look at a plot of, and this is part of your laboratory assignment, I told you to in laboratory today, I'm going to ask you for the graph of that example problem, okay? I want you to actually graph it, okay, on a sheet of rectilinear paper. It's already worked out, the example in the textbook that I told you, okay? I want you to do it so you can see and get a feel for what's going on. And then the actual problem at the end of the chapter, I don't know if there's another problem like that, but if not, then I'll try to make up a problem or come with a prepared problem so you can get some practice with these equations. So if we take this second equation here, which is also important for what we're doing, if we look at daily dose versus daily dose over C steady state, you told me that if we graph that data on rectilinear paper, not on semi-log paper, there's no logarithm or anything in the equation, that if we graph that, we should get a straight line relationship. And the slope of that line, you told me, is equal to negative Km. Just take the slope just like you've been doing. Look at the equation, see what's in the y position. So the y position is daily dose, so you're going to subtract one daily dose from a second daily dose. And then the x position, you have daily dose over C steady state, so you're going to subtract two daily dose over C steady state value in the denominator. Ain't no logarithms or exponents here because the equation don't got no logarithms or exponents. Okay. So the slope is just going to be the difference between two y values and two X values. The X value is the daily dose divided by C steady state value. So just like before when we're graphing, you graph your data. The X's are my data points, and then you take the slope and the intercept from the line that you draw, the best fit line. Okay. You don't use the data points to calculate slope and intercept unless they're on the line that you do. Okay. So we use the data to draw the line. And then once we get our line, we take the slope and the intercept of the line that we drew. Okay. Same thing. And this back extrapolated intercept here, you told me, according to the equation, is equal to V max. Okay. Now in that worked example in the textbook, for daily dose, they got an R there for rate. I explained the other day that the daily dose is just the rate of dosing. So in the textbook, in that worked example, they use an R on the y-intercept instead of daily dose. It's still a rate, it's the amount per day. They just calling it a rate, R. The rate that the drug is being dosed. Okay. Any questions about this treatment so far? Questions? Questions? Okay, I'm gonna ask you the same thing in lab today. I mean, are there any questions about what you need to do or what you should have done? If you've done it, that's fine. That's good. Okay, very good. So we'll be playing around with these relationships a little bit more in lab today. I had to skip over a couple of things in order to get to this point the last time we met, to get to these equations, because I wanted to give you something to work on for laboratory or whatever. So I want to backtrack a little bit to this Michaelis-Menten equation. If we look at a drug like phenetone, which shows dose-dependent pharmacokinetics, if we give a single dose of a drug like phenetone, a single therapeutic dose, I should say, if we look at plasma concentration versus time, I'll say the log of plasma concentration. We'll get a curve that looks something like this. And then it's starting sloping down like that. So up here where the concentration is high, okay, where it's almost flat. The concentration is going down, but early on that curve is almost flat. Okay. That elimination is zero order in that region. Zero order in this region. Okay. And then when it straightens out down here in this region, that's first order. It's showing first order kinetics. I think I mentioned to you, what's today, Tuesday, so that would have been last Friday, that in low concentrations, this Michaelis-Menten equation, the elimination, the pharmacokinetics just switches back to first order kinetics. So when the concentration gets low enough, it reverts back to first order. And we get a straight line, just like we normally see when we look at log of concentration versus time, or one compartment model. And then in this region here, this intermediate region, where the concentration is not that high and not that low, we're just gonna, I don't know what the textbook calls it, but we'll just call it mixed order. It ain't quite first order, it ain't quite zero order in that intermediate region. Okay. Okay. So I got three different possibilities here. Zero order, mixed order, and first order. What I'm gonna do is show you how each one of these three occurrences relate back to the Michaelis-Menten equation. Okay. So if we look at the Michaelis-Menten equation, let me write the equation. Oh, I got it right here on the board already. This is it right here. This equation. So this is the Michaelis-Menten equation. So we can see that when the concentration is very high relative to Km. Now we established when we met last Friday, Km is a concentration. So if the plasma concentration is high relative to Km, because Km is fixed for a given drug and a given individual, that's fixed. You can't change Km. If it's a different drug, it's going to have a different Km. Like the Km for probenecid would be different than the Km for phenetone. Okay, but within a given person for a given drug, we don't have any control over the Km value. Okay. But we do have control over concentrations because we can change the dose. we decrease the dose, we get lower concentrations. If we increase the dose, we get higher concentrations. Okay? We don't have any control over Vmax either. Okay? At high concentrations, I'm just going to say case one. Case one, where the plasma concentration is much greater than Km. Up here in this region, where the plasma concentration is high relative to Km. Keep in mind the McKellis-Menten equation. And by high, I'm just going to arbitrarily say, because I don't know if the book sets the standard for this, but I'm just going to say when the concentration here is 10 times or more greater than Km, we're going to call that high. I used to say 20, but we'll say 10. So if the concentration is 10 or 11 or 12 or 20 times higher than Km, it's going to meet this situation where the concentration is much greater than Km. Are we together? So I'm saying 10 times or more greater. If the concentration is 10 times or more greater than Km, we're going to say it meets this case. Now what's this case? Look at this McKellis-Menten equation. And you covered this before in biochemistry and in pre-pharmacy courses or whatever the case may be. It may not have made much sense. Hopefully it'll make sense after this lecture today. So if C is the concentration, which we have some control over by the dose that we give, if that concentration is real high, okay, then this denominator, Km plus C, from a clinical point of view, it's going to look just like C. In other words, when this is the case, then Km plus C is approximately the same thing as C. Just put that approximately. You know, see, I got that approximation sign? Because this concentration is more than 10 times greater than Km value. So Km plus C is going to be almost the same as just C by itself. Is that okay? So from a clinical point of view, from a therapeutic point of view, the difference between Km plus C and just plasma concentration by itself is probably not going to be of any clinical or therapeutic significance. So we can write this equation, this McKellis-Menten equation, therefore, delta C over delta T, and I'm going to get out of the way, is equal to Vmax times C over C. You see what happened in the denominator, right? We've already estimated the denominator just being equal to C. Because Km plus C is approximately the same thing as C. Bang, bang. So at high concentrations, the rate of elimination is just equal to Vmax. That's the spotted curve there. Zero order. Remember, we started out semester saying anytime we have a constant rate, that's analogous to a zero order process. But what we're saying now is that this change in concentration versus time is some constant value. It's Vmax. So that means that the drug is being eliminated up here in this high concentration region. It's being eliminated in a zero order fashion. Zero order fashion just means I'm eliminating the same amount per unit time. So if the body's eliminating 10 milligrams per hour, as long as it's zero order, as long as it's in this region up here, then it would be eliminating 10 milligrams per hour. So the first hour I eliminated 10 milligrams, the second hour I eliminated 10 more, that's 20 milligrams total. The third hour I eliminated 10 milligrams, as long as it's in that zero order region. It ain't gonna stay there because the liver and the kidney, I didn't show it here, but please keep in mind, I still have drugs being eliminated, by way of metabolism. I just don't usually draw it in this model. I got a Km value and I got a Ku value also. So I don't want you to think that this step right here is where the KEL is coming from, this McKellis-Menten equation. But I still have these metabolic processes and urine excretion processes in effect. So it ain't gonna stay up here at zero order because drug is being eliminated, but as long as that drug concentration, remember we said that the zero nonlinear pharmacokinetics usually has to do with the saturation of something, either binding or drug transport or things like metabolism. And I told you to look at that table and pay especially close attention to those drugs that are showing dose-dependent pharmacokinetics because of one of those three processes, okay? So a phenytoin might be in a couple of those those three categories, but I know that the binding, not the binding, but the metabolism of phenytoin can become saturated. But it might be in another category as well in that table I actually take a look at. But the take-home message here is that when the concentration is high, then this Michaelis-Menten equation right here just collapses to the rate of change in concentration, which is equal to Vmax. As long as that concentration is high relative to Km. It ain't gonna stay high relative to Km because we have those elimination processes that's constantly pulling drug concentration down. So eventually, that what was this super high concentration, it ain't gonna stay super high. It's coming down because of the elimination pathways. Questions? Questions? Okay. So at high concentrations, let me get my therefore sign better. So at high concentrations, the Michaelis-Menten equation just looks like this. I can't believe nobody asked a question because when this was explained to me the first time, I didn't understand. I know I'm not that good, but if you got it, you got it, okay? Because this is one extreme of the Michaelis-Menten equation, okay? One extreme, and I'm just calling case one. And by the way, don't get hung up with the case number because I could have started with a different case number or whatever. I just want you to see the two extremes of Michaelis-Menten equation. So one extreme is when the concentration is much greater than Km. Then the drug elimination is just a constant value, and that constant value is Vmax. A second scenario, I'm gonna just put case one here so you can relate it to what we're talking about. A second scenario, I'm gonna call it case two out here. A second scenario that can occur is, let me see if I can squeeze this in. Daily dose divided by C steady state. I'm gonna slam daily dose divided by C steady state. And I'm gonna call this case two, try to utilize this portion of the board. Case two. And we're gonna call case two, let case two be the situation when the concentration is much less than Km. Just the opposite, in the denominator. Remember we said the concentration is coming down, okay? So when that concentration gets low relative to Km, when the concentration gets low relative to Km, then in the denominator here, what we have is Km plus C is equal to, I'll say approximately equal to Km. You look at the Michaelis-Menten equation. When that concentration is real small relative to Km, then if you do the math, it's gonna look pretty much, from a clinical point of view, it's not gonna be of any significance. It'd be just like having Km by itself in the denominator, for the most part. Certainly there's a mathematical difference, but the bigger that Km value is relative to C, the smaller that difference is gonna be. So just like in the first situation, we're gonna say that if Km is 10 times or more greater than C, okay, then this condition applies. Is that fair? And you've already seen that this can happen because the concentration, if I give a high dose of a drug like phenytoin, it's not gonna stay high. The concentration is coming down, so eventually we'll get to the point where the concentration is much lower than Km, okay? And when that happens, we can rewrite the Michaelis-Menten equation to say that delta C over delta T is equal to Vmax times C over Km. I let the C out, it's Km. Where Vmax over Km, if Vmax is a constant and Km is a constant, if Vmax is a constant, Km is a constant, isn't Vmax over Km also a constant? Okay. So this is the same thing as some constant K times C. What does this remind you of, this last, what I just wrote? Delta C over delta T is equal to some K times C value. What does that look very close to that we studied this semester? The rate equation for what model? Q. Remember we used to have negative delta A over delta A over T is equal to K times A. It looks a whole lot like a first order process. Instead of amounts, we got concentrations. But so the difference is that first order, we'll put a sidebar up here for first order pharmacokinetics for a one-compartment model. Remember when we had the first order situation with KEL, we had delta A over delta T is equal to KEL times A, the amount. Don't look here in this model. And yesterday I was kind of proud as I walked around the classroom and I saw some folks that drew models on their scrap paper. I hope it helped. Okay, in trying to solve this problem. Okay, so this is an amount. This equation here has the same form, but it's concentration. So to get this equation here, what must I have? To get this equation from this one, what must have occurred? Yeah, it's just divided by the volume of distribution. Okay. I just divide this equation here by volume of distribution on both sides, and this would be the change in concentration over KEL times some concentration. The point I want to make here is that this V max over Km value is something that's related to KEL. Let's see if it's actually KEL or not. V max, we said in this equation is going to be concentration over time in the original equation. Now remember in this transformation equation, this V max was amount over time. We talked about that today and Friday. But in the original equation, this is concentration over time, the V max. So concentration over time, and then Km is concentration. Yep, it works out fine. Concentration. Km is a concentration, right? Everybody see that? I'm just trying to see what the units look like if I take V max over Km. So V max is in concentration over time units, and Km is in concentration units. Then when I do the math, isn't that going to come out as 1 over time? Reciprocal time? Y'all ain't talking this morning. What did I do to y'all? Okay, I'm trying to get some dialogue because come next exam and final, I can make a multiple choice question over there. So if you can see that relationship, you can see that the only pharmacokinetic parameter that has units of reciprocal time that we've talked about this semester is, the first order rate constants. Okay, KU, KM, or whatever. So what I'm saying here then is that this V max over Km in this equation is consistent with KEL. It's the same thing as KEL. In other words, at low concentrations, we simply have first order kinetics occurring. And that's what I'm trying to show here with this case too. It's just first order at low concentrations. Now the problem with a drug like phenytoin, I've said it before, and most of these drugs that show dose-dependent pharmacokinetics, that if I keep the concentration low, the drug is not going to exert its therapeutic effect. So for drugs like phenytoin and probenecid and the salicylates and those other drugs in those tables, you can't just give a low dose of the drug and come up with a low concentration. Yeah, it'll show first order kinetics, but that low concentration will not exert the desired therapeutic effect you want. So for a drug like phenytoin, it just so happens that to get a therapeutic concentration, I need to be up or near this kind of situation, case 1, where the concentration is greater than Km for it to be therapeutic. Does that make sense what I'm saying? Mm-hmm. You give a low dose of phenytoin, yeah, it'll show simple first order kinetics, and you know how to calculate KEL and all that kind of fancy stuff. But it's not going to have a therapeutic effect. Okay. So in fact, most drugs, even those drugs that we've talked about in those situations that we've talked about before, where we were calculating KEL, what's involved in that KEL is a V max value and a Km value, and we've just been calling it KEL or whatever. But most drugs are potentially saturable. In other words, most drugs can potentially show dose-dependent pharmacokinetics. You you take your aspirin tablet, which is, the dose is low, so it's showing first order pharmacokinetics. But if I gave a high enough dose of aspirin, and then I think aspirin is metabolized in the body, right? Is aspirin metabolized? I need to look it up in notes. Okay, well, I'm gonna assume it's metabolized. It's got a salicylic acid group on it, and I think that group is removed from metabolism. The point is that a drug like aspirin, to relieve a headache, I don't need to give a dose that's high enough to saturate anything. So it's just gonna be eliminated by simple first order pharmacokinetics, low concentrations. But if I gave a high enough dose of aspirin, it will begin to show dose-dependent pharmacokinetics as well, because I will begin to saturate those metabolic enzymes. We've already talked about the case of the drug alcohol, ethyl alcohol. If you just drink a thimbleful of alcohol, a shot of alcohol, it's probably just going to be eliminated by simple first order kinetics. But if you drink enough alcohol that you begin to become intoxicated, it's going to move out of this first order region back up here to dose-dependent pharmacokinetics, where the concentration is much greater than Km. And this intermediate region here, where I said mixed order, okay, if I'm trying to do pharmacokinetics and I'm in this region where Km and C are basically, they're not necessarily equal, but they're in the same range or whatever, then you need to use the whole Michaelis-Menten equation. So in this mixed order region, okay, the whole equation applies. When the concentration is high, okay, we can take the equation and make it look like just Emax. When the concentration is low, this equation right here just looks like Vmax over Km times C. Question? So in that intermediate region, we're not at one of the extremes, then we have to apply the whole equation. If we're trying to calculate concentration at a given time or the time it takes to reach a certain concentration. Questions? No? I ain't had a single question today. Golly. Don't do me no favors. Yes, ma'am.
Just want to know, in the body, when it want to apply, it automatically change to zero order and then again back to whole equation, and then again change to first order. It always happens automatically when we take medication.
The question on the floor is, does it automatically change from zero to first order kinetics? And the answer is yes. You guys have had physiology and all this kind of stuff. So these models, we're just trying to represent what's happening physiologically. Okay. So if I give a high dose of a drug, the initial concentration is going to be high, and if I've saturated something, it's not going to come from it. Let me see if this is. If I give a low dose, for the same drug, if I give a low dose, it would just do like this. It would just be first order right from the jump street. If I give a higher dose, it would do something like this. Okay? Because, like I said, these pathways of elimination are occurring. So if I give a high dose, the concentration is not going to stay high, so when it gets low enough, as a result of elimination from the body, yes, the body will automatically,
So
the body, it doesn't have to do anything. The liver, there's only a certain amount of metabolic enzymes in the liver, whatever it can be. So it ain't like it's going to automatically occur just as a result of the drug concentration getting lower and lower.
So first we give initial dose, and then at the end we have, for example, maintenance dose.
This ain't got nothing to do with no maintenance dose. Well, it could be. Because if you're talking about a drug like phenytoin, yeah, you're going to be given, it's going to be multiple doses. I'm trying to get you to see what's happening with one dose. But in these equations here, yeah, we're assuming, look at these same equations here. This is assuming that we're giving multiple doses. So the maintenance dose is done. But the same thing is going to be true if the concentration here is much less. If you look at this, we just been looking at the original equation, but if we look at this equation that we derived, the concentration is low in this equation. This is going to be V max over C. It's still going to be, first order. But now, the different one, I'm glad you asked the question because it brings me up. But now this V max over Km, this V max over Km is not KL anymore. It's clearance. It's still a constant, but it's not KL. Because remember, to get from here to here, we multiply through by the volume, right? So we multiply KEL times the volume, now V max over Km is the clearance value. Because this V max got different units. This is mass over time. This is concentration over time for V max. Okay? So if I take, let's do the same thing. If I take a mass over time right here, let's say mass over time, and I divide it by a concentration. Km is a concentration. It's kind of hard to see the way I did it. VM, I'm writing way too small, and I apologize to those in the back. Mass over time, and I divided by concentration. I know what I can do for concentration. Mass over volume. That's what concentration is, right? Mass over volume. What's the final unit going to be? If I take the units for Vmax, which are mass over time, in this equation, because in this equation it's concentration over time. Mass over time divided by mass over volume. Because Km is the concentration mass over. What's that going to come out to be?
V over time.
What pharmacokinetic parameter that we have come to know and love has units of volume over time? Huh? Clearance. Very good. Clearance. I want you to see the concept. So in this equation right here, Vmax over Km is a clearance value. In this equation right here, Vmax over Km is a first order rate constant. We can come to that conclusion just by looking at the units. So Linda, does that do it some justice?
Yes.
Okay.
Thank you.
Very good. Yeah, but I'm glad you asked that question because because the units change between these two Vmax values. In this case, Vmax over Km is KEL. In this case, Vmax over Km is clearance. We okay with that? Okay. So I think I'm gonna wind this down, and just if it'll help you with your assignment for today's laboratory, I think in that example problem, maybe one of the problems at the end of the chapter, they're asking you to calculate the dose once you know the value of Vmax and Km. So these are two key equations here. So if I need to calculate the dose for a patient, once I know Vmax and Km, and again, the reason that we have to determine Vmax and Km in a given patient is so that we can adjust the dose. For these drugs that are showing dose-dependent pharmacokinetics, it's hard to adjust the dose if we don't have some idea of Vmax and Km. For drugs that show linear pharmacokinetics, since the concentration is proportional to the dose, it's no big deal adjusting dose. Okay. So if the concentration is too high, if the concentration is 20% higher than I want it to be for a drug that shows for a drug that shows linear pharmacokinetics. If the drug concentration is 20% too high, I just reduce the dose by 20%. So at least in theory, the concentration would come down by 20%. If the concentration is 20% too low, I just increase the dose by 20%, and then the concentration should go up by 20%. For linear pharmacokinetics, first order pharmacokinetics, that's true. Not here with these drugs, dose dependent. For phenytoin, if the steady state concentration is 20% too low, if you increase the dose by 20% to try to get it up, it's going to go up way more than 20%. So if we know Vmax and Km, we can adjust the dose properly. That's kind of the idea. So these two equations are very important. So if I want to adjust the dose, if I want to calculate a dose for a patient, and I know the steady state concentration, remember now steady state is usually going to be a concentration within the therapeutic range of the drug. So if I know the therapeutic range that I'm trying to achieve, I'm going to put that in there for C steady state. Okay. Now I've calculated Vmax and Km, or I know those values, and that's what that example problem is showing you how to do when they graph those two concentrations that I told you to take a look at, okay? So you can estimate from a graph like this, the value of Vmax and Km. Amen? That's what that assignment in the textbook, the worked example, is doing, okay? They only have 2 points, I just wrote 1, 2, 3, 4. Do the same thing. In the textbook, it's only 2 daily doses and 2 steady state concentrations. So in the textbook, this is what they're looking at. And then they just, you know. In real life with a patient, you probably only going to do 2. I mean, because the more you stick and draw blood, the more it's going to cost, the more you inconvenience in the patient. So they just did 2 in the textbook in that work example. So I can get Vmax and Km. The slope is equal to negative Km. And I know Vmax and Km, so if I'm trying to calculate a daily dose, follow this. When I want to calculate a daily dose, it's best to use this equation. If you know Cmax, not Cmax, I'm sorry. If you know the steady state that you're trying to obtain, and all you want to do is calculate the dose that's needed to reach that steady state, amen? Then use this equation right here because it only got the dose in one place. So if we already know where we're trying to go, see steady state, put that value there, we're trying to reach 15 milligrams per liter. What dose is required to reach 15 milligrams per liter? Put 15 milligrams per liter here and 15 milligrams per liter here. We know Vmax and Km, put them in there, sports fans, and then solve for daily dose. That daily dose would be the estimated value that you would need to give that person on a daily basis. Now, we've already said that this is a drug that's going to be given 4 times a day, and you calculate the daily dose at 1,000 milligrams, and you're going to split that 1,000 into 4 equal doses. If it's a drug that's given 2 times a day, and you calculate the daily dose as 1,000 milligrams, then you give 2 500 milligram doses. You know, maybe 9 in the morning and 5 in the afternoon or something. Okay? So that's the idea there. Now, on the other hand, if we're trying to figure out what concentration, what steady state concentration is going to occur if we give a certain daily dose, it would be better to use this equation. If we already know the daily dose that we're going to give, you see daily doses in 2 different places, it just makes the math easy. Okay. So if we know the daily dose we want to give, and we just want to know, hey, is that going to overdose the patient? Is that going to be too little? Is that going to result in a steady state concentration that's too low? You see, that could be a clinical question too. Then if we know that daily dose and we have an idea of what we think about giving, then put that daily dose here and daily dose here. Again, we know Vmax and Km, and solve the C steady state. To see if that C steady state that you want to obtain is adequate or is appropriate. Questions? Now, you could do this. You could do the same thing with the beauty of this equation. It helps us to establish Vmax and Km from this graph right here. But in terms of calculating the dose or calculating the concentration, once we know Vmax and Km, any one of them will do. But if I'm trying to solve for a dose, what dose do I need to give in order to reach 10 milligrams per liter? What dose do I need to give? Why would I beat myself up using this equation? I'll use this equation right here. And since I say I'm trying to reach 10 milligrams per liter, just plug 10 milligrams per liter in this equation. So I'm saying just think smart, okay? Sometimes you don't have to work that hard to get to where you want to go. So if you already know the dose you want to give, then you just trying to find the steady state that's going to happen. Use this equation. If you're trying to calculate what dose to give, and you're trying to find the dose that you want to give, then use this equation right here. If you're trying to find the dose, then presumably you already know what steady state that you're trying to reach with that dose. So that's kind of the idea. Question on this. I'm gonna stop right there. Yes, ma'am.
So you were talking about phenytoin and how high it can go as far as the
I'm sorry, I can't understand what you're saying.
So you were talking about phenytoin and how high the concentration can go. How I'm just curious, how high can it go? Because isn't the therapeutic range for that 10 to 20 just like the
I think phenytoin is 10 to 20. I mean, let me just put it like this. And I don't think the book comments on it. But if we look at, this Vmax is a rate also, okay? So this has a mass per unit time on the left-hand side. If you substitute units in for all of these here, Vmax in this equation has mass per unit time units, okay? mass over time for this Vmax. This one is concentration over time. So maybe this, the question on the floor is, well, how high can, what was it, can the concentration go? Or, don't disagree with me, just ask me the question here.
I just asked my
I want everybody else to understand, to hear the question.
just how high can it go since the therapeutic?
How high can what go?
The concentration
Okay.
go.
Okay, so the question is, how high can the concentration go? Let's just look at this equation, this one, which we say we're using for the clinical situation. Under no circumstance, would we want the Vmax, I don't want to say it that way. Under no circumstance would we want the daily dose to be greater than Vmax. So like in that worked example, I think they found Vmax to be, was it 630 milligrams per day or something like that? The one I told you to work through, the worked example.
Mm-hmm.
The y-intercept. Was it 600, it was 600 and something, I think. Okay. All right, so we wouldn't want.
630.
Thank you so much. Y'all gonna be mad at me this afternoon, but I mean, I'm getting the impression that, most of us ain't even looked at it. Okay. So 600, we wouldn't want the daily dose to be, in that example, to be greater than 630, because if we look at the model here, let's say we dose 650 milligrams a day. The body ain't gonna be able to handle it, because the maximum rate of elimination in that worked example is 630. The body can't get rid of no more than 630 per day. So if we were dosing at 650 milligrams per day, towards your question, we're gonna kill that patient, because the drugs are gonna keep on building up. We're gonna never reach a steady state, because we're gonna overload the capacity of the liver and the kidney to get rid of the drug. If we establish that Vmax is 630, from a physical point of view, that means that body cannot handle, in terms of elimination and excretion, it can't get rid of no more than 630 milligrams a day. That's the maximum it can handle. Vmax. So we wouldn't want to give a dose. Usually the maintenance dose or the doses we're giving are going to be, the daily dose is going to be much less than Vmax. But we don't ever want to exceed Vmax, because that's just going to mean that the drug is going to keep on building up and building until the patient keels over. Going back to my sink example, it's like when the water's coming into a stopped up sink and you reach a steady state, it's coming in at 1 quart per minute and going down the drain at 1 quart per minute. Okay, if I turn that faucet up too high, that water level is going to keep on rising, and eventually, it's going to run over. So kind of the same thing. That's not a perfect analogy, but that's kind of what's happening here. That Vmax is actually, if it's drug metabolism that we're talking about, like in the case of phenytoin, that means the body can't metabolize no more than 630 milligrams of phenytoin every day. That's it. So if you give a daily dose greater than 630, you're going to kill the patient. That's just all it is. If there's a drug like probenecid, which is actively, that's another drug that shows dose-dependent pharmacokinetics, it's actively secreted in the tubules of the kidney. I don't know what the Vmax is for probenecid, but if you exceed that value, okay, you're going to cause toxicity of that drug, because the drug is, it's just going to overload the transport system. So in the case of probenecid, you got these carriers that are latching on to the probenecid and actively secreting it into the proximal tubules of the kidney. If you give too much of a dose of probenecid, let's say that Vmax for probenecid, let's just say it's 500 milligrams per day, the Vmax value. And I give 600 milligrams per day of probenecid. Now those carriers that's responsible for transporting the probenecid, they're not just going to be saturated, they're going to be swamped. So the drug is just going to keep on building up. We're talking about multiple dosing. I think Linda mentioned, since we're talking about steady state conditions, we don't reach steady state just after one dose usually. We're going to be giving repeated doses. So the drug concentration will just keep building up if we saturate those enzymes, or those carriers in this case, and just keep on, giving more and more drug. Any other questions? Okay, that's all I have for today. I think we can wrap this up tomorrow. I want to show you how to calculate the half-life. Because remember we said this is dose-dependent pharmacokinetics. So like the KDL value, the clearance value, the half-life, volume distribution, they're not constant. If we calculate the half-life up here in this region, it's gonna look different than if we calculate the half-life down here in this region. So tomorrow we'll talk a little bit about how to look at a couple of these different pharmacokinetic parameters and how they change as a result of changing the dose and changing the concentration.
Yeah.
Okay, then